So for this second talk, I will start talking about the weighted setting. I will spend some time introducing, and this part is joint work with Simon Jubert. It appeared on arXiv this morning, but you may not see this because it's not in AG. Yeah, so I'll start by introducing the weighted setting, and I will be sort of repeating myself for part of this talk from yesterday in a slightly more general setting, but as a teacher, half of my professional time, I think it's always a good idea to repeat things, and also it would have been less easy to understand with the more complicated weighted setting. So, okay, let me start again. So now, X is still a compact complex manifold, as yesterday, but now it's equipped with a group action of a compact torus and my Kähler metric omega 0 is assumed to be invariant under this action. And more than this, it's assumed the action is assumed to be Hamiltonian, which means the following. There exists a moment map for omega 0. So I'll recall the definition, but the details will not be very important for the talk. I'll insist on the things to remember later. So the definition is, so this function is such that for any psi in T, so in the Lie algebra, yeah, this is the Lie algebra of T, of the torus. Then this induces a holomorphic vector field on the variety X. And but you can also cook up a function from mu0 and psi, because you can, mu0 takes its values in T star, you can evaluate it, take the duality bracket at psi. And the definition of a moment map is that you have that the derivative of this function, exterior derivative of the function, gives a one form which is the same as the interior product of omega 0 with respect to psi, which means just you plug in psi as the first entry, and then you have still have one entry. That's one form. So this will not be the most important part of the definition for what I will say today, but as a consequence, the moment image, which is the image of this map, this is mu0 is continuous, and this is a compact subset of R to the R, which is a convex polytope. Basic, but I mean, very important result from Attia and Guillemin-Sternberg. The torus? No assumption. So it cannot be more than half dimensional if you want it to be effective, but yeah, no assumption. It can be much smaller. Because you have this, and then actually, for any theta closed real 1-1 form, since I'm on a compact Kähler manifold, this assumption, I also have a moment map for any theta like this. So with the same property here, but not this one. This one really relies on the Kähler assumption. So that will be useful in the definitions. Yeah. And another comment, and that's what really is important, is that this convex polytope essentially depends only on the Kähler class. So I'll consider now K as yesterday's space of Kähler potential. So I can recall this. So this is a space of smooth functions such that this is a Kähler form. But now I add the assumption that this is T invariant. Oh yeah, there. I should assume T invariant as well. Otherwise there's no moment map. Okay, so if I consider this, then for any phi in this, I can associate a moment map mu phi for omega phi such that the moment image is the same. So why will that be useful? It's because we'll consider not, a different version of Kähler geometry which involves another function, which is called the weight. And this is a function defined on this moment polytope, so it's defined on something which depends only on the Kähler class. So I introduce this function. I fix one smooth function with positive values defined on the moment polytope. And then from this, I'll consider a variant of Kähler geometry, which is as follows. So I'll consider a weighted volume form for omega phi, which will be the volume form from yesterday, the standard volume form.
KT is just the invariant Kähler potential, and we have some notation for those Kähler potentials that give the same volume.
Any. Yeah. For any psi, there's a choice of moment map. So moment map are not unique, but there is a choice of moment map that has the same image. Okay, so I take the standard volume form for omega phi, and I multiply it by a positive function, so it's still a volume form. And now, this is well defined for any phi in KT. This is a consistent way to define this new volume form on all the Kähler class omega 0. Okay, and then I tried to say this yesterday. Most of Kähler geometry is about volume forms, at least for canonical Kähler metrics. So from this notion, you can define new versions of canonical Kähler metrics. So first, new notions of curvature. So the weighted Ricci curvature. So if you remember, I defined it by its local potentials. And I said, so I defined it in terms of the complex Hessian of local potential for omega phi. But then I said that's like the quotient of the volume form with respect to the standard volume form in coordinates. So here I take the same, but with this new weighted volume form. Okay. Then, so of course this is already enough to define the analog of Kähler-Einstein metric. But I will come back in a minute. Let me first define what's needed to get a weighted CSCK matrix. So you need a weighted trace. As yesterday, the trace was important. And one of the things I said is the trace is the derivative of determinant or of the volume form. Now I do the same with this expression, and I get a weighted trace. So, so omega phi, maybe I'll just write phi. Trace with respect to omega phi and the weight v of something. This is actually the standard trace plus another term like this. Okay, so maybe not clear. When I'm writing this, I should actually, that's a composition. These are functions. Okay. But I write it like this. Okay, so now that I have the weighted trace and the scalar curvature, remember from yesterday, it was the trace of the Ricci. So now I can take the weighted trace of the weighted Ricci curvature, and I get the weighted scalar curvature. Good question, and yes, actually, that's okay, there's no that, sorry, that's why. So that was when I took the matrix and not the volume form. Okay, so here, the V, log of V, it gets out as a sum. So now, if you take this out of the log, then you get IDD bar of a global function on the manifold. So the Kähler class is the same. It's still C1x. Yeah. So from this, you have notions of, you can guess the notions of canonical Kähler metrics, but I'll explain why it gives more standard examples. So one first weighted solitons. Well, we could say weighted Kähler-Einstein, but the terminology is rather weighted solitons. And it was first considered close to this generality by Mabuchi, and then later by Bellman with Nystrom in this generality. In the general setting, but there are many examples. So this is when the Ricci curvature is a multiple of omega phi. But with the previous remark, so this is in C1x, I have automorphisms. The Kähler class cannot be, the first one class cannot be negative of 0, so I just put 1 as the multiple. Up to scaling, it is 1. It is positive. It has to be positive for this equation. So it's really about Fano manifold, this notion. And then, yeah, so examples. So the first the basic example and the most considered is the example of the case of Kähler-Ricci solitons. And that's when the weight is the exponential of a linear function. Oh, I should have said this before, but the K case is when V is constant equal to 1. But you have more interesting example in the sense they come up in geometric settings, but which are not directly related. I mean, they're not really about X. They're about other manifolds. So say X is Fano, and you consider the cone over X. So as in yesterday's talks, consider this this algebra, but you take the spect. And then this is really a cone, an affine cone. It admits a Ricci flat Kähler cone metric, as we heard about also in a short talk yesterday. If and only if X admits a weighted soliton with the weight, which is of the following form. It's an affine function to the power minus n minus 2. Now, let me add another one. So say X Fano of index R, of B Fano, sorry. I don't know, whatever. And I consider a P1 bundle over B of this form. Then this admits KE, so that's a bad example, I will say it, but this is equivalent to X equal P1 admits a V solitons with the weight of this form. Some power of an affine function. X is P1 is the fiber. So that's not a very good example because it never admits KE metric, but could consider variance. You could consider Kähler-Ricci solitons on this, and then you would have corresponding weighted solitons exist. And this is part of a general construction which are called semi-simple principal fibrations. I will not talk about this much, but this was introduced by Apostolov, Calderbank, Gauduchon, Tonneson, Friedman. At least when the fiber is toric. And so this is a very large class where existence of canonical metrics on the total space of the fibration reduces to existence of weighted canonical metrics on the fiber. So that was for solitons, and then there's as well weighted CSCKs. So now I have to consider another function defined on the polytope. And the weighted CSCK is a metric which satisfies this. Oh, right. The scalar curvature, the weighted scalar curvature, is equal to this fixed function on the moment polytope. And for example, if V equals 1, W equals to S bar, gives you the standard CSCK. If V equal 1, W is affine, gives you Calabi extremal Kähler matrix. And then you can do more. Again, I have this construction. But let me stop here for examples. So you still have a variational approach, and I can go fast on this. Now, with yesterday's lecture, I have a weighted Mabuchi functional which is now defined by, so again, it's variations. And I take the natural variation on the previous definition. Instead of putting the S bar, I take W. And instead of putting the scalar curvature, I put the weighted scalar. And then I put also the weighted volume form, as that is to be expected. Okay. So we have some of the properties from the standard Mabuchi functional that hold. I will come back to this later. So now again, repeating myself, I want to introduce the weighted delta. I have to introduce the variance of the previous functionals, the standard functional, so I have a weighted entropy. So what should I do? I replace the volume form by the weighted volume form, and that's okay. And weighted J functional. So now that's why I had this weird notation with the 1. The 1 was to say V equal to 1. So now I have these functionals in general, where this is defined by its variations. Check. So I replace the trace by the weighted trace. And here I add a constant. Now I put some weight. Any questions? Yeah?
In a geometric setting, do you have a metric aspect? Do you always need some complexity or concavity of
Of the weights? Not yet. For results of existence, yes, we will need some assumptions like this, but it's more of a, so it's a problem of what we are able to do in the analysis. There's no fundamental reason why we should consider weights with certain convexity properties. And the behavior are quite different between this one and the other one. Yeah. That's a good question. So this will come up later in the statements. So now I want to use this, again, these functionals to measure coercivity. And I will take this functional where v tilde is a certain weight, defined as follows. So d log of v of x times x. So why do I take this weight? So that's not a complete justification, but at least why is this weight a natural player here? So assume omega phi is a weighted soliton. Then if I look at the weighted scalar curvature of omega phi, and I have my soliton equation there, and the definition of the weighted scalar curvature over there, then this is equal to the trace, the weighted trace of omega phi itself. And from the definition of the weighted trace, this is the trace of omega phi with respect to omega phi. Plus this term. And this is equal to n, whenever I take the trace of a colorimetric with respect to itself. So this is, in the end, this is v tilde applied to mu phi. So this weight, v tilde, is very natural from the point of view of weighted solitons. And it turns out that it's the good measure of coercivity that I may say more about this later. Okay. So now I can I can define my weighted delta invariant with these ingredients. But there's something I should, I must define two variants.
Somehow responds to like the Mabuchi and one norm, but just with this weighted magic.
Probably, probably. Yeah, but I didn't check, yeah. Yeah, so that was true for yesterday's functional with no weights, but that was exactly, comparable to this. Okay, so now the definition of the delta. So I fix a subgroup of the reduced automorphism group that commutes with T, but that's not so important what it is. Actually, I will take only the trivial group or the complexified torus, which acts on X. With this assumption, I can complexify the action. I get an action of C star to the R on X. Okay, and now I define my reduced delta invariant, weighted delta invariant, as follows. So this is the best coercivity constant for the weighted entropy, but now I have to be careful about this group. Instead of plugging in directly the functional that measures the coercivity, I have to take the inf over an orbit of the group G. If G is trivial, and that's nothing, it's just same, but in general I have to do this, and this is such that G the image of omega phi by G is as scalar potential phi G. Okay, so for now it's just a definition. Why is this the right definition? Because we have a version of the theorem from yesterday, the Zhang's characterization of existence of soliton of Kähler-Einstein matrix in terms of analytic delta invariant. Now we can do this for weighted solitons. But we need something. I'll comment on the assumptions. So I need to consider a large enough torus action. I need to assume that the weight V is log concave. Then we have the equivalence between the existence of a weighted soliton for this weight This is equivalent to two conditions. One is in terms of the delta. This, the TC1, TC reduced version should be strictly bigger than 1. And the other assumption is the weighted Futaki invariant vanishes. In a minute. Yeah. So the proof is actually the same as yesterday, so I will not give details. But, I mean, there are subtleties that introduce the assumptions, and it is essential to consider a reduced version of the delta invariant. So why? So we have to use a version of Tian's theorem to go from coercivity of a Mabuchi functional to existence of Kähler-Einstein metric. So this is due to Han and Lee. Which says that there exists a V-soliton if and only if the Mabuchi functional for W equal to the weight V tilde over there is TC coercive, and TC coercive means this notion over there. And for this statement, you need the assumption that the torus is maximal. And they don't have the assumption on log V, V log concave. But I mean, for smoothness, if you want a smooth weighted solution, soliton, then there's a gap in the proof of smoothness. So you have to add the assumption if you want smooth solitons. So this is for the assumptions and also why we consider the reduced version. But why we have to consider this TC coercivity? That's because the functional MVW in general, this is linear along TC orbits with slope given by the Futaki invariant. Oh, this is a fine. Yeah. The weighted Futaki invariant. Okay, so that's a definition of the Futaki invariant, if you want. And that is telling you that if you want coercivity, then the slope must be 0. If you have something linear, you want it to grow to infinity, the slope must be 0. You want it to be bounded below at least, the slope has to be 0. And now, yeah, if the slope is 0, you cannot be strictly coercive, and that's why you have to consider this variant here. Then, yeah, the proof is the same. You use the Chen-Tian formula for this, which exists, and you compare with this functional, works the same. Oh. Any questions? Yeah? There exists, because this tells you that if you have a minimizer of the Noguchi functional, you actually have a full TC orbit of minimizers. So you never have uniqueness. I mean, it could be invariant, but it does not happen on compact manifold that there is a non-compact group of isometries. So now for the rest of the lecture, the end of the lecture, I want to sort of justify the following claim. So it's not a mathematical claim, but philosophical maybe. So the precise value of delta is important. Not only the fact that it is strictly bigger than 1 or not. And also I put really omega 0, not only C1 of x. I'm claiming this is important for other classes. So we'll see for other variants, not the analytic version. Why? We'll have other illustrations of this, but let me give 2. So first, motivation. I will not spend time on this for lack of time, but I give the statement, and it's I mean, it's in the non-weighted case that many of you may know this result, at least in the algebraic setting. So define another number to be this. I take the largest real number S such that the class, cohomology class, C1 of x minus S times the Kähler class of omega 0 remains a Kähler class. Okay, and then the statement is that the minimum of this and the delta invariant with the trivial group G, this is equal to the so-called Gratus-Ricci lower bound. So the set, the Gratus real number such that there exists a Kähler metric in the Kähler class omega 0 such that the Ricci, the weighted Ricci of omega phi is bigger than t times omega phi. Here this inequality means the difference is Kähler.
So this equality holds for any compact.
Yes. Yeah, any Kähler class, any compact Kähler manifold. And it's about twisted Ke metrics. So I can rewrite this, and that's actually part of the proof as the sup of all t smaller than this S. So now I assume straight away that this is Kähler class, so that for all theta in C1x minus t omega 0 Kähler, there exists phi such that Ricci v of omega phi minus t omega phi is not only Kähler, but equal to this prescribed Kähler form theta. That's these are interesting Kähler metrics themselves, twisted KE metrics. So here I'm doing everything in the smooth setting, in Kähler setting, twisted smooth Kähler. But you could consider twisted KEs, for example, with currents of integration, and then that corresponds to log K stability, for example, log Fano. So that's relevant to algebraic geometry as well. I mean, okay, the statement is not saying that you can put anything. The statement is saying with smooth Kähler, but it has implications for other twisting forms, currents. Okay. And now the second motivation is another theorem which gives, so now, okay. So this was about the G equal 1. And actually this is always, okay, if you take omega 0 to be the first Schoen class of a Fano manifold, this is always less than 1 because of the same reason as here. So this is more of an information about K unstable case, if you want. Now we want another type of thing, a sort of positive results. And I'll give an existence sufficient condition for weighted CSCK metrics. So I have more assumptions and yeah, maybe some setting before. Well, let me include it in the theorem. So V, W are weights, as before. So V takes positive values, W maybe not. I assume that the Futaki invariant vanishes. I assume, again, that the torus is maximal, that V is log concave. Let epsilon be a strictly positive number, and set delta epsilon for, I mean, to simplify notations, I introduce delta epsilon as this. So I take the reduced weighted delta invariant of omega 0, and I take something slightly smaller, so that I have coercivity of the entropy for this value, delta epsilon. Now, I'm sorry about the notations. The condition is not so easy to state, but it exists. Ooh. Yeah, I consider the Kähler class. What is it? Delta epsilon omega 0 minus C1x. So, okay, sorry, I said Kähler maybe. For now it's not Kähler, but it will be in a minute. Okay, no, it is Kähler. I assume it's, sorry. Okay. Let me write this correctly. was missing on my notes. Got it wrong. I assume first is, I mean, not first, but next in a series of assumptions, I assume that this Kähler class is Kähler. This class is Kähler, sorry. Okay. Now I can write what I was starting to write. I consider a function which looks like a weight, which is defined on a product of polytopes. The expression, for now, it's not important. It will come in the sketch of proof why we have to consider this. Then that's not all. I still have assumptions to add. So in terms of this function here, and there are two situations. First one is x equal to p1, omega 0 equal to c1x, and this function is strictly positive. Or second set of assumptions, less nice. So now I assume this is a Kähler class. So any Kähler form inside of it has a moment polytope. Okay, I fixed one. Actually, there's no choice because I fixed one here. And for C1 of x, there's the canonical choice of moment map. But yeah, that's the moment image of this Kähler class. Sorry, this one, no, because you have, I mean, I would be very careful. You could hope for some Minkowski difference of polytopes, but I would be very careful about that. I prefer not to say anything. Yeah. Okay, so finished writing the hypotheses, but they're not enlightening. What's important is just that everything that appears is in terms of the weights and the delta invariant, nothing else. And I'll finish with a sketch of proof of this. So before that remark, the situation A, it's about P1. It's actually non-empty, really non-trivial, because of the construction I mentioned earlier, this vibration construction. So from weighted metrics on P1, you can build lots of canonical Kähler metrics on higher dimensional manifolds. And in situation A, the assumption is really simple. I mean, it does not mean it's always verified, but it's simple to write out if you know the weights. Oh, sorry. Yeah, there's no conclusion. Sorry. Thank you. Then there exists VW CSCK metric in omega 0. Thank you. So the sketch of proof will look suspiciously similar for the first steps to the previous one, the one from yesterday as well. So first we delegate the passage from coercivity of Mabuchi functional to existence of CSCK metrics to other people. Actually not, because Simon is one of the authors, but so this is already okay. Bye. Dineza, Jubert, Ladili, and Han and Liu. Under our assumptions, if this Mabuchi functional is coercive, then there exists a VW CSCK metric. So this first step is, as always, okay, but now we have to ensure that this is coercive. Oh, by the way, yeah, I forgot one name. I try to write references often. The notion of weighted CSCK metrics is due to Ladili. And this work, both works rely on previous works on Ladili and on the Mabuchi, weighted Mabuchi functional, for example, showing that it is convex along weak geodesics and this sorts of thing. Okay, so now, what do? I use the Chen-Tian formula, also due to Ladili. And I use the definition of delta. So this is bigger than, okay. Put quotes. Because I should put the inf, but essentially that's what we can get from the delta invariant. And then a nice property of these functionals is that it behaves linearly with respect to theta and w. So this is bigger than this functional, mv delta epsilon times v twiddle minus w and delta epsilon omega 0 minus Ricci of omega 0. So now it is enough to show that this is coercive. Now, using the same proof as on Monday, I can also do the following reduction. If I take theta in this class, any theta in this class, and the difference between the two is bounded. Same argument as yesterday. So it is enough to show that this is coercive. I can choose the theta. Now, running out of time. I do only situation A to finish. So one last result before that. So if theta is a Kähler, this functional is convex along weak G out of 6. This is also due to Ladili. Then it is bounded below if there exists critical point. And the critical point is a solution to a new equation this one. And this is called the weighted J equation. And now you enter, well, if you know about this, in a non-weighted case, the J equation, the J flow has been studied a lot in order to apply this strategy in the classical case. So you can try to adapt their techniques to show existence of a solution here. So here it only proves bounded below, but since I took epsilon strictly positive, I can upgrade bounded below to coercive quite easily. So that's not a problem. And yeah, I just have to show that there exists a solution to this. It is in general very hard. And not much studied from the algebraic point of view, if you want a subject of study. But there is an easy case, which is case A. So this equation writes, so I'm in dimension 1. So this is theta divided by omega phi plus b log v mu phi mu theta equal to W. And then this is actually a weighted Calabi-Yau equation. Check. Yeah. Okay, but that was not W, that was, sorry. I'm about to finish. This is this equation, which is a weighted Calabi-Yau and much easier to solve. And W hat is delta epsilon V tilde minus W. So what appears here is exactly this function evaluated at mu phi, mu theta. So that's why we have this assumption is coming. Okay, so sorry for going over time. If I can give one sentence more. So there are open questions, there are perspectives. So I said, study these equations for the algebraic perspective. Also, I do not give a theorem of Zhang saying this delta invariant is the same as an algebraic version. That's open. And then a challenge, compute this invariant for P1. Even for v equal to 1, I don't know. I can give a strictly better than 1 estimate, but no more.
Let's find the big